So in this video, we're going to talk about the equilibrium constants for weak acids, the equilibrium constants for weak bases, and the equilibrium of weak acids and weak bases. We're going to define a few things related to that, primarily our Ka and our Kb for the equilibrium constant for dissociation of weak acids and weak bases in water. Let's consider a 0.05 molar solution of nitrous acid. Right? Nitrous acid is a weak acid. And so it's going to act differently than what we've dealt with up until now. If we put nitrous acid, right, in solution, it, instead of dissociating 100%, it will create an equilibrium between hydrogen ions and nitrite ions. Right? And so, right, if we start out with an initial concentration of 0.050, right? None of that. Our change, this is an equilibrium, is going to be minus x. We're going to be plus x, plus x. And when we reach equilibrium, we'll be at 0.050 minus x, x, and x, right? So that is an equilibrium, right? We have established an equilibrium among those species. And so we can define an equilibrium constant for that, right? So the equilibrium constant for an acid dissociation is going to be equal to products, concentration of hydrogen ions, times concentration of the other anion, the conjugate base anion, if we were talking Bronsted-Lowry, divided by the concentration of undissociated acid. Right? Generically, we could put it like this. Concentration of hydrogen ion, concentration of anion, divided by concentration of undissociated acid. Right? And so this becomes an equilibrium problem, and we've defined a new equilibrium constant, the Ka, the equilibrium constant for acid dissociation. Okay? So the question is, how do we measure the value of this equilibrium constant? We need to find one of these concentrations, and this is what we did in the laboratory too. We find that if we use a pH meter and measure the pH of this solution is 2.37, okay? So since the pH is equal to the negative of the log of the concentration of hydrogen ions, right? That means the negative of the pH is equal to the log of the concentration of hydrogen ions. And so that means 10 raised to the negative pH is equal to the concentration of hydrogen ions. Okay? Okay, so if our pH is 2.37, then we can find our concentration of hydrogen ions by raising 10 to the negative 2.37, and we get that our concentration of hydrogen ions then is 4.266 times 10 to the minus 3 molar, right? But that's equal to x, right? So now we can go back and find our Ka by putting in x, 266 times 10 to the minus 3, and that would be squared, divided by 0.050 minus our 4.266 times 10 to the minus 3. right? And so if we calculate that Ka out, we get approximately 3.98 times 10 to the minus 4, right? And that is typical for the Kas of weak acids. Normally these Kas of weak acids are small numbers, right? They are exponents of 10 to the minus 3 or larger, or 10 to the minus 3 to 10 to the minus 10 or 12, depending on the strength of the acid. And so we're going to deal with equilibrium constants that are very small numbers, right? Our Ka expressions are very small numbers for these weak acids. Okay, so let's consider a weakly basic solution. So let's look at this compound, right, which is called methylamine. Right? Methylamine is a weak base. If we remember, right, from before, weak bases often don't bring their own hydroxide ions to the party. They've got to create hydroxide ions by reacting with water. And so the methylamine is no different here. So we've got to take our methylamine, right, dissolve it in water, let it react with water to create the methyl ammonium ion in water plus hydroxide ion in water, right? And so that becomes our equilibrium. And, we can write an equilibrium constant expression for that. Right? If we write an equilibrium constant expression for that, our equilibrium for our weak base, Kb, is going to be the concentration of the methyl ammonium ion in this case times the concentration of hydroxide ion divided by the concentration of the unreacted methylamine, right? Remember, because water is liquid, its activity is 1, and so, 1 doesn't affect our fraction, and so we can leave it out. And so that it becomes an expression for our dissociation constant, equilibrium constant for the dissociation of a base, a weak base in water, our Kb, right? So if we've got this reaction then, we can express our, if we know our initial, we know our change, we know our equilibrium, we're starting with, 0.04 molar of the methylamine, Water is a pure liquid, so we don't worry about it. We're starting with 0 of the methyl ammonium ion and 0 of the hydroxide ion, Some of this is going to dissociate, make some of that, and some of that. And so we at equilibrium, we have a little bit less of our methylamine and a little bit more, or we've made some methyl ammonium ion and hydroxide ion, and then we can substitute those in, X 0.040 minus X, Okay, so here's our essential information transferred over to another slide, So we've expressed our equilibrium concentrations, but we need to find what X is. And so we go, into the lab, we make the measurement, we make this solution, and we find that the pH of this solution is 11.60, And so we find from the pH, we can find that the concentration of hydrogen ions is going to be equal to 10 to the minus 11.60, Or the concentration of hydrogen ions is equal to 2.512 times 10 to the minus 12th molar. Okay, but that's hydrogen ions. And remember, this is the concentration of hydroxide ions. So we have to use then our Kw, right? Our Kw, right, is the concentration of hydrogen ions times the concentration of hydroxide ions. So we have 1.0 times 10 to the minus 14th is equal to our 2.512 times 10 to the minus 12th times our concentration of hydroxide ions. If we solve then for the concentration of hydroxide ions by dividing both sides by this, then we end up that the concentration of our hydroxide ions are 3.981 times 10 to the minus 3 molar. So now we have our concentration of hydroxide ions, which is X. Right? So here we are, continuing with our essential information. So now if we want to find the Kb, right, our Kb is going to be, right, X is 3.981 times 10 to the minus 3 molar. And it's X times X on that side, so we can square that, divided by our 0.040 minus 3.981 times 10 to the minus 3. Right? And I guess since we're in an equilibrium constant expression, we don't really have to show the units, right? Because these are technically activities, which come up unitless, right? So then when we do our math, we get approximately 4.4 times 10 to the minus 4 is the Kb for our weak base, right? So now let's consider a 0.020 molar solution of sodium nitrite. When we defined weak bases, we said that one of the things that can act as weak bases are salts of the anion, the conjugate base anion of weak acids, right? So if we look at this, right, it is a sodium salt, so we know it will dissociate completely, so we always consider complete reactions or processes first. So our complete process is going to be our sodium nitrite dissociating to form sodium ions and nitrite ions, right? And right, if our initial is 0.02, then our change, because it is a complete process, is going to be all of that reacts in a limiting reactant problem, or all of that dissociates. And so we end up with plus 0.02 and plus 0.02, right? Now, sodium ions aren't going to do anything, right? But then we consider equilibrium processes, right? Once we've done complete processes, then we consider equilibrium processes, right? And so if we go up here to the nitrite ion, right, we know that the nitrite ion was the conjugate base anion of nitrous acid, right? We already considered this equilibrium. Right? So the nitrite ion wants to stay in equilibrium with some nitrous acid, right? Those two should always be in equilibrium with each other. Well, since we don't have any hydrogen ions to react with, They have to take hydrogen ions from something in order for this reaction to reach equilibrium. And so what they take hydrogen ions from is water. So our equilibrium is nitrite ion reacts with water to make hydroxide ions plus nitrous acid. Right? And so we can consider that equilibrium, and that's why, right, making those hydroxide ions, that is why the nitrite ion can act as a weak base. We just have to now consider, right, how do we relate that to the other things we know about nitrous acid? Okay, so we get ourselves to this equilibrium expression, which we can express as a base equilibrium, right? Our Kb, equilibrium for this as a base reaction, is going to be our concentration of hydroxide ions times the concentration of our nitrous acid divided by the concentration of unreacted nitrite ion. Right? That is an expression of our Kb. The problem is we don't know what that number is, right? Since nitrous acid, right, is a common acid, we can find the Ka, but how does that relate to the Kb? Well, let's look at a particular situation here, right? If we look at the Ka for right? So if we look at our acid dissociation, right, we can write our Ka as concentration of hydrogen ions times concentration of nitrite ions divided by the concentration of undissociated nitrous acid. Okay? So we will start there on the next slide. Right? So here's our essential information that we've kept. So let's look what happens if we multiply our Ka, right? Our Ka times our Kb, right? That's going to be equal to, right? Our Ka is concentration of hydrogen ions times concentration of nitrite ion divided by the concentration of undissociated nitrous acid. And our Kb is hydroxide ion times concentration of nitrous acid in equilibrium divided by the concentration of nitrite ion. Right? But if we look at this, we've got nitrous acid in the denominator here and in the numerator here, right? Those two, nitrous acid divided by nitrous acid is 1. Similarly, we've got nitrite and nitrite, right? Nitrite divided by nitrite is 1. And so that leaves us with only, right, Ka times Kb equals the concentration of hydrogen ions times the concentration of hydroxide ions, which is equal to our Kw, which as long as we're at 25 degrees is 1.0 times 10 to the minus 14, right? So that means that always Ka times Kb for the same species, right, for the related species, is 1 times 10 to the minus 14. We can use our Kw. So since we know the Ka for nitrous acid, we can find the Kb. So here we are with our essential information. We found earlier that our Ka for nitrous acid was 3.98 times 10 to the minus 4, right? So the Kb is going to be equal to 1.0 times 10 to the minus 14 divided by 3.98 times 10 to the minus 4, and we get, right, for the Kb, we get 2.51. Why are my 5s coming up funky today? 51 times 10 to the minus 11 is the value of the Kb. So now we know the value of the equilibrium constant for this reaction, and now we can do a calculation with that reaction. But I think this video is getting long enough, so we'll save that for the next one.